So I assume that all of you can see screen. And remember, so if I just go to the beginning, what we have done last Monday, so let me start from there. So we started talking about general theory of relativity, and so remember that we have talked about three key principles that are important to prove the field equations, and also to understand the concepts behind the general theory of relativity. And those are principle of equivalence and principle of general covariance. And the third one is principle of consistency. And we discussed about the principle of equivalence using a thought experiment, which is 4 scenarios that are related to an elevator. And then we actually understood what principle of equivalence means. And then we talk a little bit about principle of general covariance, right? And so the idea is the laws of physics should be the same in all inertial and accelerating frames. And so, by the way, I am actually sharing the screen with you, and if you cannot see it, then please let me know, right? And so here actually we discussed that we should be, in order for the principle of general covariance to valid, we should be able to explain these general relativity physics laws in terms of valid tensor equations, right? And then we had principle of consistency, and the idea behind that is, as an example, when you have these general relativity laws, they should be reduced to Newtonian mechanics under appropriate conditions. And also for the laws of special theory of relativity, if you convert curved space into flat space, right? So that is the idea. And then we learn a little bit about space-time and how this Minkowski space metric is converted to the general metric, which is G mu nu. And then we had some discussions about the covariant differentiation, how it works in general relativity. And then we learned about how these laws of conservation momentum can be written in general relativity, where you have this equation 2 right here. And finally, we talk about energy momentum tensor, and there are actually 16 components in the energy momentum set tensor. So just to give you an idea, I briefly discuss about each of these components and what kind of things that they explain. And then there was so we use this particular diagram, and then so I showed you how to derive some of these components, like each component and different symmetries associated with this energy momentum tensor. And I guess this is, and then we had 2 special cases for this energy momentum tensor. So the first one is called dust. So what happened to this energy momentum tensor, how it is reduced under dust, and also when you have a perfect fluid, right? The reason that we are discussing these 2 particular situations is that we will meet these 2 conditions very frequently, right? So by the way, this dollar mark shouldn't be here, so it's kind of a mistake, right? And for the dust, So we discuss what are the conditions. Dust is the collection of non-interacting particles and they are at rest. And because of that, when you talk about all these conditions, we can tell that the energy momentum tensor will be reduced to this form right here, where you can see this equation 4, right? So which means you will have only the first component of the tensor and all the other components will be 0. This is due to the fact that all these non-interacting particles are rest basically, and I have explained it why you get 0 components except the very first one. And then we talked about this perfect fluid, and under the perfect fluid there are 3 conditions. Perfect fluid is basically dust plus pressure, and then you have 0 viscosity and 0 heat conduction. And under those conditions, you can again reduce the energy momentum tensor to this form right here, which means you will have only diagonal terms, right? Because when you do not have this, when you have a 0 viscosity, the idea is you don't get the shear stress terms, right? So that's the idea. And then you will only end up with, since you have dust plus pressure, you will have all these diagonal components where the pressure is represented, right? So that's how it is reduced. And then I guess this is where we stopped last time. And then I briefly explained about this covariant divergence of the energy momentum tensor, where you get the divergence is 0 in curved space-time. I think that has been discussed before as well. Right. Today I am going to derive or discuss about the Einstein field equations. Right. Now, all the mathematical components that we learned up to now, which means about starting from these manifolds, we talked about covariant vectors, contravariant vectors, and then about tensors and different laws that can be applied for tensors, and how to write a tensor equation and how to transform a tensor. So we learn all these things, and then we discussed and actually did some examples to learn how to find these connection coefficients, which is specifically important when you have, it's not like the flat space where you have constant vectors, especially unit vectors. And so at this particular point, you have to differentiate all these vectors, and then we learn about the covariant differentiation, contravariant differentiation, and then we discuss how to find these connection coefficients or Christopher symbols. And after that, we discussed about a Riemann curvature tensor, how to find the components of the Riemann curvature tensor, and then about the Ricci tensor, Ricci scalar, all these things, right? And last week we discussed about energy momentum tensor, right? So what we have actually done up to now is just discussing the components that we need to discuss about Einstein field equations. And today we are going to use all that knowledge to discuss about the field equations and derive an equation which is known as Einstein field equation, right? Now, rather than directly giving you the field equations, let me discuss with you how Einstein approached, not how Einstein approached, how we can understand this field equations and how we can see that how Einstein thought about that, right? Now, in the heart of Einstein's mind, what he needed is to find the correct relationship, such as let me say that A equal B, something will be equal to something else, right? So that is an equation. So what he was always thinking is to find the correct relationship. Find that he thought that maybe there is a relationship like A equal B, and then he needs to find what is A and what is B, right? Now, according to his theory, he knows that there is a source for the gravity, and that because of that source, the space gets curved, right? So that is the idea. So for one side, you should have the curvature of this space-time, and the other side, you should have the source, right? So that create that curvature. So that is the idea. Now, if you think A as the component that curves the space-time, so he thought that, okay, A is the field equations that describe the curvature of the space-time, right? So let's see how can you write curvature of the space-time later, right? So this is where you have to get involved with these Riemann curvature tensor, Ricci tensor, those kind of things, right? Because those are the tensors that mathematically explains the curvature of space-time, right? So that just keep that in mind. And then the part B, what is in the right-hand side, should be the mass energy source of the curvature, right? On the left-hand side, mathematically, you should have some components or equations that describe the curvature of the space-time. Now, on the right-hand side, what you should have is the source that creates this particular curvature of the space-time, right? Now, what he understood is, let's say B as the mass energy source that creates the curvature, right? So now the next question is, we need to find exactly what is A and what is B, right, to give this relation. Right, now we know the two things that we should have in the left-hand side and right-hand side of this Einstein field equations. Now, to have the correct relationship, there are certain conditions, right? Number one, this expression should be a valid tensor equation, right? So that is because if you remember that according to this principle of general covariance, what we are expressing here should not be coordinate dependent, which means it should not change from one coordinate system to the other coordinate system. Therefore, we should be able to write it as a valid tensor equation, right? So that is number one, and this is why we started to learn about basics of tensors until this point, so that we can use it here. And the other thing is, should not contradict with any of the fundamental laws in physics, right? So that is second condition. And the third one is, under appropriate conditions, it should approximate the Newtonian description of gravity, right? So these are the three conditions that has to satisfy in order to have a correct relationship. So when you put something for A and when you put something for B and make an equation, that equation has to satisfy these conditions to be a valid equation, right? So that's how we can think about this, right? Let's see. One thing that we know is T mu nu, which is the energy momentum tensor that we explained last Monday. That describes the total energy of a physical system. Remember that it had all these 16 components, which basically tells you all different types of sources of energies, right? And because of that, we can think that this T mu nu, which is the energy momentum tensor, can be a good candidate for the source for the gravitational field. So, which means we can assume that maybe T mu nu is what we have as the source, like, which maybe can be equivalent to that B that we talked in the previous equation. And the other thing is, there is something else that we also know, that is the metric tensor is important for describing the curvature of a Riemannian manifold, including four-dimensional space-time. So metric tensor is G mu nu. Right? Remember that we told that for the Minkowski space, which is a flat space, the metric tensor is meter mu nu. Right? And we change it to G mu nu when we explain curved spaces. Right? So maybe that Riemann curve, this metric tensor describe the curvature of space-time. Right? So which means, so he thought maybe a good relation will be this one. So in the left-hand side, you have the metric tensor, which describes the curvature of the space-time. And on the right-hand side, you have a constant, and this constant is named as kappa, and the energy momentum tensor. Right? He thought that maybe the energy momentum tensor is the source of the energy, and that source will curve the space-time, and that curved space-time may be represented from this metric tensor. Right? I mean, there is nothing wrong with that, right? Thinking it in that way. But the problem is, right, so one thing is that, so from the previous results, we can actually show that the grad mu T mu nu equal to 0, and also grad mu G mu nu equal to 0. So which means the equation is nicely balanced because both sides become 0. Right? And if you need why I wrote these two, just look at the equation 2 in the note, which gives you the equation grad mu G mu nu equal to 0. And this one, the second one, that mu G mu nu equal to 0, that comes from the section 4.4 about the metric compatibility that we discussed, I guess, in the last week. So this is related to the previous lecture. So we have discussed all these things before. So which means it's fine up to now, but there is a problem that which we have not discussed. That is, this doesn't reduce to Poisson equation, which is the Newtonian gravitation. Now, we may not have actually talked about the Poisson equation for the Newtonian gravitation, but there is a Poisson equation that we can actually deduce from Newton's theory of gravitation, which is like grad squared phi equal 450. So that is the Poisson equation for the Newtonian gravitation, which I have not mentioned here, but we will learn it in the next lecture. Right? But the problem with this equation is that when you try to reduce it to the Newtonian gravitation, it doesn't work. Right? Now there is a condition that any equation that you write for the as the field equation should be reduced to Newtonian gravitation under appropriate conditions. Right? But that doesn't happen for this equation. So that is the problem. And because of that, this equation is rejected. Right? And he looked for different options after that. Yes. And so the second option may be that we know that energy momentum tensor describes the total energy of a physical system. So which is again a good candidate for the source for the gravitational field. So we will keep it in that way. And the other thing we know is not the metric tensor. However, the Riemannian curvature tensor that we talked before, R, mu, alpha, beta, gamma, it contains all the information about the curvature of a manifold. Right? So we have discussed about that. So maybe we can compare, or maybe we can relate these two then, right? Instead of the metric tensor. Right? I mean, when you derive the Riemannian curvature tensor, if you remember the equation roughly, the metric tensor is inside that. Right? Actually, we can take the Riemann curvature tensor and write an equation like this. So the Riemann curvature tensor equal to kappa times energy momentum tensor. So we remove the metric tensor here, G mu nu, and then replace the Riemann curvature tensor. Now then we have to think about, is it okay to write it in this way? Now I need an answer from you for this equation. Is it correct to write in this equation? Or is there anything wrong with this? What do you think? Is it right or wrong? So there is a question mark at the end, right? Whether it's okay to write this equation. I mean, is it correct mathematically to write it in this way? And this should be related to the knowledge that we discuss about basic things about tensors and those kind of things. So that's why I asked about that from you. Right? Please give your answers and also the reason, right, why it is not correct. And then I can discuss about that after that. Right? So these are like very, very fundamental things. So that's why I asked from you. Just if you remember what we have discussed previously, you can comment on that. Nobody knows the answer. Maybe anyone who did like tensors for double math, maybe they know the answer, right? Tarang or Nirmal. I mean, all the others should know about that because we talked about, basic tensor laws. Now, actually, I expect these things for you to know, right, when you go into exam. Right? So basic things about tensors. Like just once you write this tensor equation, I just want to check with you whether this makes sense for you or whether this is right or wrong to write it in this way. Now, how about the rank of the tensors in the two sides? So if I make it a little bit easier for you. How about the rank of the tensors in two sides? Now just tell me the rank of the tensor in the left-hand side. What is the rank? Is it rank 1, 2, 3, 4, 5? What is the rank at least? Now you need to provide an answer in order to continue this discussion, right? Otherwise, only that I am talking. Right, so I got one answer. That's that seems to be close and make sense. And how about the others? Naveed, do you have an answer? Nirmal, Pangajeeva. Right, so I have an answer for the rank for the tensor now. So at least what is the rank of the tensor which is in the left hand side? That is the Riemann curvature tensor R mu alpha beta gamma. Now just give me the answer for that one at least. What is the rank of that tensor in the left hand side? It is not hard to answer, right? What is the rank of that? And remember there is something called type of a tensor, and the other one is the rank of the tensor. Type is basically like how many upper indices and lower indices that you say that for this one, the type is like 1,3. So what I am asking is a rank of the tensor. Now all those who are actually not answering here, so I am assuming that even though your name appears here, you are not here, right? So that's why you don't know what I am talking. So it's just, I just would like only 2 of you are trying to answer and others are just, completely silent. So you don't have any idea what I am talking, right? So that's what I can understand from here. Right, so I have another answer for the rank of the tensor. Right, for all others, make sure that you actively participate when we are doing something, right? At least discussing. Right, so there may be issues that you may not be able to clearly communicate the message due to internet issues and something like that. So that's okay. Other than that, try your best to participate with what we are doing, right? And right, so I can see that most of you have understood that the rank of the tensor in the left-hand side, which is the Riemann curvature tensor, the rank is 4, right? Remember that we discussed and defined what is the rank of a tensor and the type of a tensor, right? So I expect all of you to have that basic knowledge, right? Please, right? And on the left-hand side, on the other hand, you have this energy momentum tensor written as T u nu, and you can clearly see that it's a rank 2 tensor, right? So these 2 tensors assign to different ranks, right? Let's see what has happened here. So let me go to answer for you. And see that I think the Sajini, what you suggested is, I mean, somewhat correct, because when you have this Riemann curvature tensor, when you compare it to T mu nu, you have to contract the Riemann curvature tensor, right? Because it's, two different types of tensor, two different ranks that you have the tensor, so you cannot equate those two. And because of that, so let me go back to the slides. So you can see that you cannot equate these two, right? I mean, it doesn't work in that way. So the two tensors are in two types. And because of that, what we know is you can contract Riemann curvature tensor to get the Ricci tensor, right? So remember that we learned about that. I don't know whether you can remember it or not. So when we talk about the curvature, let me go back here for the previous note. Yes. So this is the place where we talked about Riemann curvature tensor, which is RLIJK, and we talked about the properties of the Riemann curvature tensor, and after that we contracted it to have the Ricci tensor and Ricci scalar, and the Ricci tensor is R mu nu, right? So we can see that it makes sense, right? So it's a rank 2 tensor. Instead of rank 4, once you contract it, you get the rank 2 tensor. And for this reason, Einstein had high hopes about this Ricci tensor, right? Because that, you can make an equation out of that using the energy momentum tensor. So he suggested another equation, that is R mu nu, which is the Ricci tensor, which will be equal to kappa constant times the T mu nu. And so he suggested this as the candidate for the field equation. And using this equation, actually the Einstein was able to resolve the problem of slight variations in the Mercury's orbit. Does anybody know what this means, like slight variations in the Mercury's orbit? Now, if you look at the orbit of the Mercury, so let me try to share a video with you, which may explain this better than what I try to convey here. The orbit of the Mercury has a different path because it has a small wobble in its orbit, which means when it goes an elliptical path, the next elliptical path is slightly rotated, right? And the next one is again slightly rotated. So there is a wobble in the path of the Mercury, and this difference cannot be accounted using Newton's gravitation theory. And what has happened was in 80s, 50s or close to something like that, people were thinking about that because they were, using Newton's gravitation, they were able to explain all these orbits of the planets. However, the Mercury, which is the closest orbit for the Sun, has a different scenario. It has this small wobble, which means it will follow elliptical path, and the next time this elliptical path will be rotated a small amount, and the next time again it will be rotated like that, right? And because of that, they had this problem how to explain it. And this rotation is, a very tiny amount, as far as I remember, 43 arc seconds per century or something like that. And what has happened is, they thought maybe this is due to the gravitational effect coming from the other planets, like how people discovered this Pluto. Pluto was not initially discovered, and then Pluto or Neptune, I can't remember which one of these, the last two planets. So they discovered it based on the gravitational effects coming from the other planets. They predicted there should be a planet at this particular point, right? So that's how they predicted. So they thought about maybe the same reason apply for this orbit of the Mercury. But what has happened is this, even though you accounted those small gravitational effects from the other planets to think about this wobble of the Mercury's orbit, they still had a discrepancy, which means there is still a difference, about 43 arc seconds or something like that, which they couldn't explain. And then the next idea came as that there may be another planet. So there is another astronomer who suggested there is a planet called Vulcan or something like that, that very close to the sun. So this name came, that Vulcan, that name came because it's the origin of the word volcano, right? Which makes sense for a planet that is very close to the sun, right? And this planet Vulcan came into the picture, and then one astronomer explained that because there is another planet like Vulcan very close to the sun, which will make this bubble of the Mercury so big. But then later they identified that there is no planet like that, and because of that we cannot explain it that way. And after that, in 1916, when Einstein was deriving this equation for the field equation for the general theory of relativity, he explained that this small bubble comes as a result of the curvature of space time due to the huge mass that is close by, which is sun, right? And there is a small video, like a 5 minutes video, that explains this. And let me try to play it right here so that we will get a better idea about it. Can you see? Let me reshare this screen. Okay, so what I was explaining here is, so Einstein had this equation which relates the Ricci tensor with the Einstein's, the Ricci tensor with the energy momentum tensor, and eventually what Einstein did was he had to remove that equation as well, because when you take these covariant derivatives, they don't match up, right? And then he rejected that equation and came up with the new equation, which is the final one in 1915. So that was actually this equation, R mu nu minus half Rg mu nu equal minus kappa times T mu nu, right? And if you need, you can write the same equation in the covariant form. So that means you lower the indices and write the same thing. So what I was mentioning is here, the equal sign came down here for some reason, but there is nothing specific about that, right? You can put it in one line if you need. I mean, that's how we usually write it. And in this equation, what you have is Riemann curvature, sorry, Ricci tensor, and the Ricci scalar is right here, right? Rg mu nu and minus kappa T mu nu, and k equal 85g over c to the power 4, which is the Einstein constant. And then actually, to make it more compact and understand and remember it easier, we define another component called Einstein tensor, which is capital G mu nu, and that is defined as R mu nu minus half Rg mu nu. And this is actually the left-hand side of this equation, right? So this whole thing we defined as the Einstein tensor and write as G mu nu, right? So when you look at even in the internet for different books and different things, you will see this Einstein field equations in few different forms. And one form is this one, and then also in the covariant form sometimes. So regardless of different forms, you should understand that as the Einstein's field equations, right? So that's why I have all these different forms mentioned here, so that when you see it in somewhere else, you should understand it basically gives you the same thing. And then you define the Einstein's tensor G mu nu, which is defined as R mu nu minus half R times G mu nu. And this, the first R mu nu is the Ricci tensor, and just R that you have is the Ricci scalar. Right, and using that, you can directly write the Einstein equation in this way: G mu nu equal minus kappa times T mu nu. And sometimes people use this geometrized units where you equal G and C to be 1 and rewrite these equations. So that is G mu nu equal 8 minus 8 phi T mu nu, right? So remember, this comes as a result of K, which is equal to 8 phi G over C to the power 4. So once you make this G and C to be 1, K will be equal to 8 phi, right? So it's not K, actually this is kappa. And then you can write it in this way, because C and this other term is G and C are both equal to 1. Right? I mean, you know, these are just different, you can scale the equation in this way. And sometimes you can write 8 phi G equal to C, which means this the complete equation. I guess for some reason in the slides, once you get the note, you will write it in. You will see it in the correct way. The way that you write it, this one here is actually. This is, so right here you can see that when you make G and C equal to 1, you can write G mu nu equal to minus 8 phi T mu. And sometimes you use this form as well, where you make 8 phi G equal to C, so which makes this kappa equal to 1, right? So if that is 1, you can directly use it in, write the Einstein equations in more compact form. So that is G mu nu equal to minus T mu nu, right? Sometimes people write it in that way as well. And all these forms are correct. So they are written under different, different scaling parameters using different, just like different ways of using it. And the reason that I put all those forms is that sometimes if you are interested in read different books, you will see different forms, right? Some people use like G mu nu equal minus T mu nu because it's kind of compact and kind of give you the all the things in the compact form so that it is easy to remember. But some people use this more extended version, and sometimes you see this one right here, minus 8 phi T mu, like that. So all these terms, you can see that these are like different forms of the same Einstein field equations, right? Right. So here actually, so when I write it, for some reason it may have came into two different rows right here, but you just write G mu nu equal to minus T mu nu, right? So that's how you write it. And you will see it in the correct form in your notes. Right, now the next thing is, so there is a problem for you, that is to show that this Einstein equation R mu nu minus GR mu nu will be equal to minus KT mu nu can be written in the form that is given here, right? So you can actually try it, and I will have this on your tutorial, next tutorial, but you can ahead of time, you will try, you can try it, right? And so that's another form that you can derive based on what you have for the Einstein equation. Right, so that's one part. Now let's look at this section about the cosmological constant. Now this is actually, the story actually gets very interesting after this particular point. Now Einstein have his field equations that already derived. Now all the hard work is done. And as you see that we actually spend around maybe, more than 10 hours or 10, maybe 10 days or 6 to 7 days to derive all these things, start from the beginning, like tensors and everything to come up to this point. After that, so I have a section called cosmological constant here. I guess this topic should go into this particular slide. So in 1917, which means after 2 years, Einstein proposed a modification to his field equations, right? So he suggested an additional term. So there's a small mistake right here. So let me correct it. So what he suggested is, he proposed a modification to his field equations, and he suggested an additional term. So that is this lambda g mu nu to his equation. So he add this term to his equation, right? So without, proving or anything like that. And this particular term is called cosmological constant, right? And this is very popular nowadays in cosmology. However, at that time, anybody knows why he added this term to his equation? Is there like any reason for that, to add this? Actually, the reason for adding this new term is he believed that the universe should be static at that time, right? So he was thinking that the universe should be static, should not change. Now, according to his previous equations, when he derived all this mathematics, he probably have seen that staticness of the universe does not represent from his equation. So he was not happy about that. So maybe he had this constant to the equation, right? To make it to make the universe static, right? So that is the reason that he did this. So he was happy about that at time. Right. Now, as the gravity is an attractive force, it is possible that one day the universe collapses onto itself, right? Now, in general, we used to tell now that the universe is expanding. I can remember that we talked about the Hubble law, which tells that the universe is expanding, but at the same time, we know that everything is attracted by the gravity, and because of that, it is possible that on one day the universe can start to collapse right onto itself. And so Einstein didn't like it. So he introduced this cosmological constant in order to prevent the collapse, right? So that's the idea. He thought that, if there is only gravity, so this can collapse one day. So maybe I should put this constant here. So he put the constant to prevent the collapse of the universe. And what actually cosmological constant explain is something like an anti-gravity, like a repulsive force for the negative force or a negative pressure, which will, cancel out this collapse that could happen with the gravity. So that is his idea, right? So that's what this cosmological constant means actually. But the problem is, now this is his modified field equation, by the way. So instead of having r mu nu minus half r g mu nu equal to minus k kappa times t mu nu, he added this extra term, which is the cosmological constant times g mu nu. And you can see that even when you add the cosmological constant, you have to add this metric tensor, right? G mu nu, right? Mathematically, you should understand why it is, because if you just have this constant, then the equation is not again balanced, right? You should have the same rank for all the tensors, right? those are actually basic things that you should look at for the equation, right? So I expect at the end of this lecture series, these basic things I expect that you should know, right? Like when you write a tensor equation, so you should make sure that it's a valid tensor equation, right? By looking at all these, ranks and everything. However, so the Einstein's final equation after the modification is this one right here by adding a constant. But something different happened in 1929. After 14 years, he derived these equations. As you remember, I think we have talked about the expansion, the Hubble's law, when we were talking about galaxies. So the Hubble discovered that, so there is this mistake here. Right. So the Hubble discovered that the universe is expanding, right? And we all know that from Hubble's law, all the galaxies are moving away from us, and he derived the Hubble law, which tells us that the universe is expanding. Now what happens? So the problem is now if the universe is expanding, it is found that this expansion is consistent with the original solution of the unmodified field equation, right? So actually his previous equation was correct according to the situation that they had at that point. The only thing is when Einstein was deriving these equations in 1915, he thought that the universe is static because nobody knew or there were no experimental evidence at that time that the universe is expanding. It is after 14 years in 1929, Edwin Hubble discovered that the universe is expanding, right? I guess we have discussed about this under galaxies when we were doing astronomy part. Now, because of that, when he discovered this expansion of the universe, we can see that the original solution of the unmodified field equation is consistent with that, which means agree that now this equation does not agree with that, right? Now, so Einstein was very unhappy about that, and he used to state that this adding this cosmological constant for his equation is the greatest blunder that he did at that time, right? Because it was not there. So he is the one who added it, right? Eventually in 1929. So they figured out it is not correct. However, with the time again, so this is like a story, right? So I could just refer the note, and I have mentioned everything here. In 1998, we had some observations from the Hubble Space Telescope that showed that the universe is actually not only expanding, but expanding at an accelerating rate, right? And we will actually discuss about this Big Bang theory towards the end of this, in the coming lectures. So you will learn that how we can tell that the universe is accelerating and everything. But for here, as a fact, just get my word that in 1998, observations from the Hubble Space Telescope, and I will explain that how this accelerating thing discovered in later, but they have found in 1998 that universe is not only expanding, this expanding actually happens in an accelerating rate. So then this concept or the term dark energy came into play, because one way to explain this expansion is to use hypothetical dark energy that permeates in all the space. Right? Should be that. Right. So now you have dark energy, and I don't know, we have, if you remember that we have talked something called dark matter before, right? Now students get confused with these two terms. You need to make sure that there are two meanings for these two terms, right? It's not like, these two are two different things. The dark matter is something responsible for attractive forces, right? Because dark matter is normally you found in galaxies and galaxy clusters, especially for this galaxy rotation curves. If you remember that we talked about dark matter, which is responsible for this mysterious matter that you cannot see. However, the effect feels similar way as you feel the gravitational force. Because of that, that is called the dark matter. However, this dark energy means the dark energy is actually responsible for this accelerating expansion of the universe, which is basically a repulsive effect that you have, right? So those are two different things. Right? Make sure that you understand it. And now we used to think that this cosmological constant may be described using this dark energy, which he put, right? And because of that, Einstein may be correct at the end, putting this cosmological constant. Because his idea was that universe is static, and to make it static, he applied the cosmological constant. And then Hubble came out, and having the Hubble expansion law, he actually discovered that the universe is expanding, that you don't need the cosmological constant. However, now we have a different scenario that we found that this expansion is accelerating expansion, and because of that we need something. And they have this hypothetical dark energy now that permeates in all this space. Now to explain the dark energy, we may need the cosmological constant again, right? And because of that, Einstein may be correct. And you can see that this discovery of dark energy came out in very later, so it's still like very new to us. I mean, not that much new, but still it's not that far away. It's like 20 to 22 years. I don't know, maybe I don't know whether you were here when they discovered the dark energy, right? However, the idea about the dark energy, their physical meaning is a complete mystery still, and people think that there may be something called vacuum energy that is responsible for the dark energy, but we still don't know about that, and we will discuss about dark energy separately in coming lectures, right? So this is this is the discussion actually at the end of. This is so we have come today at the end of the discussion about the Einstein's field equations, right? Now, anybody have any questions? Now, this discussion actually get more and more interested when you go into the next sections, right? So I think we did the hard part, like deriving all these tensors and everything, but make sure that you understand that mathematics and you can do those as well. But from here on, what we will do is we are going to use the things that we learned up to now about the Einstein field equations and metric tensor, Riemann tensor, Ricci tensor, and we try to do the calculations, and we will try to discuss about different phenomena that we can discuss. For example, we will be discussing about the black holes, what happens in the vicinity of a black hole, and we can nicely explain those using something called Schwarzschild metric that we are going to look at in the next, probably not in the next day or within the next week, we can probably look at and discuss about the Schwarzschild metric. And under that, we will look at two different phenomena called gravitational time dilation and gravitational redshift. And if you were in my lecture for this general degree not last month, yesterday, so I was discussing about these black holes and different phenomena that can happen. And actually, I have explained what gravitational redshift and gravitational time dilation means. But for you, I will be actually deriving those equations using the Schwarzschild metric on the next, within next 2 days. And one thing that I also need to discuss is how you can reduce this Einstein field equation under weak gravitational field, so that you can explain that you can get the results. That is the Poisson equation for the gravity, Newtonian gravity, right? I will show that this Einstein field equations can be reduced to the Poisson equations for the Newtonian gravity under a weak gravitational field on the next day. And apart from that, we are going to discuss something called Friedmann equations after that. That is also to discuss about different models of the universe, whether the universe, whether we are in open universe, closed universe, like that. We will be try to, if time permits, we will derive the Friedmann equations using a different metric, using the field equations. And then we will discuss about different models of the universe. And at the end, we will go into discuss about the Big Bang theory and this expansion of the universe, dark energy, and those things, right? So that will be the plan for your next, coming lectures, right? Right. Anybody have any questions up to here? Right. So keep in mind that this part of the lectures is very interesting. So it is important that you get involved. It's something, a field that you normally don't touch frequently, but at the same time it's interesting, right? And the other things, you don't get the chance to learn it from anywhere else, right? So this only comes in your special degree under physics, right? So make sure that you understand it. And